Okay, this is what we're going to cover in Unit 5. There's a lot here. What is a solution? There's quantitative solutions and qualitative solutions. Acids and bases are solutions. So we're going to talk about what is an acid, what's a base, both qualitatively and quantitatively. Okay, so let's start with qualitative. This question will be on your final. Yeah. Monday. And it's on stoichiometry. And that both simple stoichiometry, like going grams to grams, or the limiting reactant, which I did. Yeah. Yeah, and I gave you a whole bunch of practice worksheets out the yin yang. Those are all good candidates, including the dry lab for yeah. Okay. Now, know how a salt crystal dissolves. I'm going to talk about that in a second here. But first of all, what is a solution? You've heard this word a lot. Normally, when people think of solution, they think of a water solution, like salt in water, sugar in water, coffee in water. I always think of water, but a solution is not limited to just water. A solution is 2 components minimum, a solute and a solvent. There's only one solvent, and whatever is minor to that, quantity-wise, is called the solute. And it has to be homogeneous. I'll give you an example of a solution. Vodka. Vodka is half water, half alcohol. Can you see the difference between the alcohol and the water if you looked at in vodka? No, it just looks like plain old water. So that's what I mean by homogeneous. Vinaigrette, oil and vinegar. Can you see the differences between the two? Most definitely. So that is not a solution. So that's heterogeneous. So it's got to be homogeneous. Okay, but it's not limited to liquids. Your ring, and if you have a gold ring on your finger, that's a solution of copper and gold. You can't see the difference between the copper and the gold. So it's homogeneous. And there's other things in there too, but it's mostly copper and gold. And the copper's in there to make the gold harder, because gold is very soft, wears very poorly. If you see an older person that got married very young and they have a wedding band, frequently it's worn down to hardly anything, unless they started with a huge wedding band. Gold is not very hard at all. Okay, and then we have 2 kinds of solutions, polar and non-polar. Polar has to do with the kinds of atoms that are on the molecule. Usually if it's got oxygen on the molecule, it's polar, like water, for example. Water is very polar, H2O. If it doesn't have oxygen on, usually it's non-polar, like ethane, no oxygen at all on it. Or gasoline. Gasoline is mostly made up of octane, which is 8 carbons and 18 hydrogens, no oxygen at all. So when you put gasoline and water together, what happens? The lighter one floats on top of the heavier one. Gasoline is lighter than water, density-wise, but it's not a solution either. So the deal is, and remember this, if you don't learn anything in this class, remember this, like dissolves like. For example, if you have some oil on your car and you want to get it off, oil is very non-polar. What do you want to use to get it off with? Something polar or non-polar? Non-polar. So you don't want to use water. So water is very polar. Put water in there, what happens to the water? It just beads right off. So you can use something like vegetable oil, very non-polar, Vaseline, non-polar, anything that's non-polar gets it right off. The problem is if you use something that's really viscous, like Vaseline, Vaseline will take the oil off. The problem is then you have Vaseline on your car. The other option is to use something that has both polar and non-polar in it, like soap. So when you wash dishes and you want to get rid of that grease, the water doesn't get rid of the grease, the soap does, because the soap is part non-polar and part polar. So it acts like glue, gluing the grease to the water. And then down the drain it goes. So you had a question. Yeah, that's a whole chapter. And I just wanted to briefly talk about it for solutions. No, no. But basically, if something's got oxygen in it, usually it's polar. Like water is mostly oxygen. That's a too little light hydrogen in it. So it's mostly dominated by oxygen. So it's very polar. So like vegetable oil, hardly anything in there, oxygen-wise. So it's non-polar. And if you just remember that as far as our class, that's all you need to know. And it won't be on the test either. Okay, like dissolves like. All right, so let's talk about what happens. What happens when we put a salt crystal in water? Now, if something is polar, it tends to be wanting to grab hold of everything around it, electron-wise. So it becomes a little more negative than it normally would be because it's grabbing electrons from its neighbors. So in this case, with water, the oxygen here is trying to grab hold of the electrons on the hydrogens and pulling them closer to the oxygen. So it makes the oxygen more negative. Not a -1 charge, a little bit more negative. And that's what this little squiggly line means. That's a Greek letter for delta, lowercase delta. And at the same time, it makes the hydrogens a little more positive because the electrons that were associated with the hydrogens now are closer to the oxygen. So oxygen basically is kind of lopsided. It's got a little negative side, and it's got a little positive side. So when a crystal of salt is submerged in water, what happens is the water starts working on the sodium and it starts working on the chloride, starts pulling it apart. That's what dissolving means. So as the water bumps up against a crystal, the negative oxygen is attracted to the sodium, grabs hold of it, pulls it out. The hydrogens, being partially positive, grab hold of that negative chloride ion, pulls it out. So that constant bumping against the crystal and that attractive forces between the opposite polarity is what makes the crystal dissolve. So what would make it dissolve faster? Huh? Temperature. Because what's temperature? It's measurement of movement, right? So the more movement, that means it's going to hit the crystal more often. So if you slow things down by cooling it down, it takes longer to dissolve. Cold coffee dissolves sugar slower than hot coffee. So there are two forces at work here. There are two competing forces that are competing together. For the dissolution, dissolving of that crystal, it is the solvating force. That's totally a function of the solvent, in this case, water, and a force called crystal lattice force, which is the force that keeps the crystal together. And whenever stronger, it'll either dissolve or not dissolve. For example, let's take sand and water. Does sand dissolve in water? No. What that means is the crystal lattice force is stronger than the solvating force. That's why it stays together. In the case of salt in water, the solvating force is stronger. The crystal lattice force is not temperature dependent, solvating force is. Okay, one way to make that dissolving of the salt crystal go faster is temperature. Because temperature says how much energy, how much motion does that molecule have? Higher the temperature, more motion. So statistically, it's going to hit the crystal more often. The other is physical agitation. When you got your coffee and you put sugar in it, normally what do? Stir it. Physical agitation, which is the same as increasing the temperature, motion. And the other one is which dissolves faster, granulated sugar or powdered sugar? Powdered sugar does. Why? The surface area, because it's smaller, the surface area is greater. Because this is a surface phenomenon we're talking about here. The salt ion, sodium and chloride, can interact with the water only on its surface. So if we break up the salt into little bitty pieces, there's more surface, so the dissolving can go faster. So there are three factors that affect the dissolving: temperature, physical agitation, and surface area. Increasing any of them will make the dissolving go faster. If you increase the temperature, increase the physical agitation. In other words, when you're stirring it a little bit or stirring it a lot. Surface area. Big chunk versus a same amount of mass, but in little pieces. It'll dissolve faster. Powdered sugar, granular sugar, a good example. And that's the qualitative part of solutions. Okay. A good characterization now, sand is something called silicon dioxide. That's the same thing as glass. And silicon dioxide has extremely strong crystal lattice force. That means it doesn't matter how hot that water is, it's not going to dissolve the sand. We can crank up the temperature. We can take the sand and crumble it real finely. None of that works because of the horrendous crystal lattice force. Okay. Okay, I'm going to I'm going to do a little getting into the quantitative side of things, let's talk about how do you measure, with this solutions now, how do you measure the solute concentration? We measured it in terms of moles per liter of solvent. And that term is called molarity. Now, those of you who did wet lab yesterday, you noticed on the bottle the hydrochloric acid had a 3M. That's measuring concentration. That's 3 moles per liter of HCl per liter of solution. And the solution includes solvent plus solute. There's another term that's used in solution. It's called molality. There's molarity, and then there's molality. Molality is much more specific. It's moles of solute per kilogram of solvent. And sometimes they're the same, and usually they're not. And what the deal is, when you do something called colligative properties in chemistry, you work only with molality, not molarity. When you're doing acid-base reactions, you're working with molarity, not molality. That's a 1A, 3A topic, not a Chem A topic. So we're not going to do anything with molality in here, just molarity. Okay, so I'm going to do one example of a typical problem you'd run into. So when you're doing molarity calculations, you have to know 2 things. You have to know moles and liters. If you're given grams, you can calculate the moles. So now whenever you see molarity, it's a capital M also. It's an uppercase M. Frequently, it's bold-faced, and I usually underline it as well, as opposed to meters, which is a lowercase m. We have uppercase M molarity, lowercase m meters. So moles of solute versus moles of liters of solution. Okay, so liters of solution, we have 345. Moles, we have grams, we have to convert. So first step is convert grams to moles. And that's that. And then this is going to go here. So you can do this all in 1 step or do it in 2 steps. Most students like to do it in 2 steps. Calculate moles first, and then throw that over the liters. So we have so that's 7.7 times 10 to the 7.0 times 10 to the minus 2 moles over 3.45 liters. We can't leave it like that, though. It's per 1 liter. or 1 liter, not for 345. So we have to do one more quick. So we have to divide the 7.7 times 10 to the minus 2 by 345 so that it's per 1 liter. So it's 2.23 moles per liter. So things like acid, when you buy acid, it's always how concentrated is it? Like, for example, muriatic acid used in pools, HCl. That comes as 12 molar in a concentrated bottle. And then you dilute it as to whatever concentration you want. It's much more economical to buy concentrated acids than to buy diluted acids, because then you're just buying water. It's also important to, when you're disposing of acids, to concentrate them. Because when a company comes and disposes of your chemicals, they do it by the weight. So if you get rid of the water, you're paying less. Okay, so that's your intro to Unit 5. As you can see, it's very similar to Unit 4 in terms of lots of mole stuff. Okay. Are there any questions about this? Yeah. This calculation here. Let me see. Let me redo it. Make sure I got it. Let's see. It's yeah, so am I. And then that divided by 345 is thank you for pointing that out. Okay, that is going to be it for today.